Alright, so before we get started, I just want to make it known that this is for educational purposes only, and no one should ever do this. So, what we have here, got some wires hanging out of a wall, and we're going to be explaining how to use a multimeter and what tools you should be using to verify that voltage is not present before you start working on circuits. So first off, I think everyone's seen one of these by now, and what they do is they beep whenever there is voltage present. Now, these things are also known to give false positives and false negatives, and these really shouldn't be used to identify whether or not a circuit can be safely worked on. These are more purposeful for helping identify what breaker maybe something's on, and you can kind of hold it up there. Hear it beeping, someone turns off the breaker, and then the beeping goes away. These should never be used to verify if voltage is present or not before you start working on a circuit. What you do want to use is a multimeter. So the first thing I do when I get my multimeter, anytime I ever get my multimeter, is I set it to continuity or tone. I make sure my leads are all the way pushed in, and I touch these together, and that verifies that my leads are working. Okay, so we know our leads work with the multimeter. We know everything is ready to go and plugged in. Next, you'll set your multimeter to volts. Now, the official way to do this is to test this on a known live circuit and then start working on whatever you're going to be working on. That's the way you're supposed to do it. So, we've got the hot here. We've got the ground. And we've got our neutral. Now, what you want to do is you want to go to your known hot and preferably to ground. That's ideal. And also then to neutral. The way neutral works is the neutral is the return path of the circuit, and the ground is designed to be attached to anything that could potentially become energized. The ground's job is to get current back to the neutral. A lot of people have trouble understanding that. I can explain it in other videos a little better, but the basics is that the ground and neutral are essentially the same electrically. The ground and neutral are bonded together at the first means of disconnect, and if current ever does get on your ground, it can then take it to the neutral so that it can go back to its source, being the power company's transformer, go through the windings of the transformer, go to the hot, find that breaker, and then trip it. That's essentially how an electrical system works during a fault. There's a little bit more to it, but that's pretty much the basics of it. So the reason why we have a ground is for it to be tied to anything that a human or somebody could be in contact with that could potentially become energized. The ground itself does not generate enough current to trip a breaker. You yourself do not generate enough current to trip a breaker. It's very important you understand that. The only way that you can get shocked is if you have a potential. I'll show you. We're going to use this for informational purposes only, just so you can see where the electricity is, I guess you would say. we've got it on. We know that our circuit is hot. I'm going to stand up and get off this floor. The floor is wood. I'm going to stand up and get off this floor. My shoes are electrical hazard rated. And I'm what you would call a qualified person to work on electrical. Do not do this at home. Alright, so there's our hot. Now, you can see that there's voltage present. In this hand is the voltage detector. I'm going to grab this hot wire. The current is going to flow through my body, but I'm not going to get shocked because I'm not touching ground. Watch. I'm going to let go now. I'm going to do it again. On, off. Current is flowing through my body to my left hand over here. And this is picking it up through my body. The same thing works with electrical when you become energized. Except that in most cases, humans themselves are grounded already. They're not wearing electrical hazard shoes. They're not standing on wooden platforms. That's why you always want to attach grounds to anything that comes with a ground screw or a ground wire. Usually that thing is metal. In some roundabout ways, you might be in a plastic box, but at some point that does go back to something metal. It's very important to attach your grounds, and now you know why. Thanks for watching. So we've got it set to volts AC. One on the hot, one on the ground, and you see we're getting 120 volts, I hope. Nominal, 120. And the same thing to neutral. You always want to check hot to neutral and hot to ground. You could have an open neutral where you're only getting a weird voltage. Maybe 30 volts to the neutral, but that hot has 120 on it, and when you complete the circuit, or you make the potential being the difference, and you are the ground, you are going to get 120 volts. See, 120 volts here to ground. In this case, my neutral is hooked up properly, so I'm getting 120 volts to my neutral as well. Certain circumstances, sometimes your neutral's not connected correctly and you don't get a full 120 volts. That's why it's very important to test hot to neutral and hot to ground. On a switch, when a switch is on, you will read 0 volts. Just like if I stick both of these leads in the same hole on the same wire, you're going to get 0 volts. You're essentially on the same line. If this is my wire, one connection point here and one connection point here, it's the same voltage. So you're going to read 0, because when you measure voltage, you need a difference, you need a potential. So when the switch is off, you will read 120 volts if you're in a house, 120. But if the switch is on, you will read 0. Now you know.